Okay, now we're going to talk about how molecular shape and polarity work together. We've talked about polar bonds, but a molecule itself can be polar as well. If we have a very simple molecule, a diatomic molecule where there are just two atoms, if the bond is polar, then the whole molecule is polar, because there's only that one bond. In a hydrogen chloride molecule, the chlorine is more electronegative, and so it pulls the electron density away from the hydrogen. We could draw it like this, where this cloud represents the electron density. There's higher electron density around the chlorine than there is around the hydrogen. So the chlorine end of the molecule has a partial negative charge. The hydrogen end has a partial positive charge. So the molecule is polar. If you put this in an electric field, you can get all the little molecules to line up by applying an electric field to it. When you have more than two atoms, a polyatomic molecule, then determining whether the molecule is polar or not is a little more complicated. The polarity depends on the geometry and, of course, on whether there are polar bonds. So we'll look at the polar bonds and see whether they cancel each other out or not in the polarities. Let's look at carbon dioxide. Carbon dioxide has two carbon-oxygen double bonds, and each of these bonds is polar because oxygen is more electronegative than carbon. So in this bond, the oxygen is pulling the electron density over here to the end, but in this other bond with oxygen, that oxygen is also pulling electron density away from carbon. And so we've got extra electron density at this end and extra electron density at that end, and a little bit lower electron density in the middle. But that makes for a symmetrical molecule. You don't have one end of it being negative, right? Both ends are the same. The carbon dioxide molecule is linear, and Vesper theory predicts that. So what we have is a force pulling electrons this way and an equal and opposite force pulling the other way. It's a little bit like playing tug of war. So if you've got one guy here, let's draw pictures. So you got one guy over here pulling, and you've got another guy over here pulling. And so he's pulling in this direction, and this one's pulling in that direction. They're equally strong. Is that carbon atom going to move? No, it won't move. Now, if this guy was weaker and this guy was stronger, then the whole thing would move to the left. But because they're equal and exactly opposite, nothing happens. So we say that those dipole moments cancel out. The bonds, the dipole moments in the bonds oppose each other, right? So, any questions about that? This is the easiest one to understand, the linear molecule with two opposing dipoles. Dipole moments are actually vector quantities. A vector is something that has magnitude and direction. When we deal with numbers, numbers have magnitude, of course, but the only direction quantity they have is positive or negative, right? And so we could also think of this as being like a number line. Let's draw a number line over here. So here's 0, and here's +5, and here's -5. And so if you have equal magnitudes but opposite directions, then when you add them together, they add up to 0. +5, and you add -5, and you get 0. It's the same idea. But vectors take it away from that one dimension into 3 dimensions. Okay? So vectors have direction and magnitude. In terms of dipole moments, we're talking about the magnitude being equal to the difference in electronegativity between the two elements. You could have a larger dipole moment if the difference is larger. And then the direction is going to point to the more electronegative atom. And this is where the geometry of the molecule comes into play. Let's look at water. So here's the shape of water. It has a bent shape, right? That's because of the two lone pairs on the oxygen. Each of these bonds is a polar bond. Hydrogen is less electronegative, oxygen is more electronegative. So the oxygen pulls on the electrons. The electrons are not shared equally. So we have a vector going in this direction and a vector going in that direction. Those two vectors are not going to cancel each other out. It results in a net vector equal to this dashed line. So we have a net vector or a net dipole moment going in that direction. So I think that, this tug of war and pulling on things is a helpful analogy. So here we've got oxygen, big strong oxygen, very electronegative. And here we've got puny little hydrogen. And so they're having a tussle over something. They're pulling. Oxygen's winning. But oxygen's also fighting with another hydrogen. And so it's like you're pulling on two people. You're pulling against both of them. The net movement is that all three of them are going to move this way, right? Even though these guys are pulling off at an angle, there's a net movement. It's not like with carbon dioxide where you have equal and opposite forces. You got people pulling on each arm equally strong, and so nothing happens except you feel like your arms are being pulled off. Does that make sense? So water is a polar molecule. If we look at its electron density, the hydrogen end of the molecule has a slight positive charge, and the oxygen end has a slight negative charge. Any questions? So to find out if a molecule is polar or not, we first need to draw the Lewis structure and figure out what the molecular geometry is. And that's what we've been talking about up until now. Then determine if the molecule contains polar bonds. Indicate any polar bonds with vectors pointing toward the more electronegative atom. The length would be proportional to the difference in electronegativity. And then decide if the polar bonds add together to form a net dipole moment. If the vectors add to 0, the molecule is nonpolar. If there's a net vector, then the molecule is polar. So you can have a molecule that is nonpolar overall, but it has polar bonds, like carbon dioxide. If all the bonds are nonpolar, then the molecule has to be nonpolar also. But you also have combinations where you have polar bonds and a polar molecule. So to really grasp this, we need to talk about vector addition. Some of you will be fine with this. Others of you will be like, don't talk to me about this. So if you're in the second group, don't worry, I have kind of a cheater shortcut that'll get you through it, okay? You don't have to think about vector addition, but I do want to cover this. So in one dimension, vector addition is like adding positive and negative numbers. It's much simpler. The vectors have to lie on the same line in one dimension. So you assign a direction, and then you add the vectors. So if we have a vector with a +5, we're saying that to the right is positive, +5 and +5. When we add those two together, we get a larger vector in the same direction. Does that make sense? Two magnitudes going in the same direction. If we have, actually let's jump down to example 3. If we have those same two vectors, but now one of them has flipped its direction. So we've got one going to the negative direction and one going to the positive direction. We add those together, the net is 0. Everybody okay with that? If we have a small vector in the negative direction, -5, and a large vector in the positive direction, plus 10. When we add those together, the sum is plus 5. Okay? Anybody have any trouble with that? Okay, what if you have more than one dimension? The way to do this visually is to draw a parallelogram. So draw your vectors that you're adding so that they start at the same point. So here vector A is going up at this angle and vector B is coming over here to the right. The directions could be anywhere, right? Because we're not limiting ourselves to one dimension now. We're going three-dimensional. In this example, it's two-dimensional. So we've got this one going that way and this one going that way. And then you draw a parallelogram. So you take the end of this vector and you draw a line that's parallel to the other vector. And then from the end of this vector, you draw a line that's parallel with that one, and they're going to intersect here. The sum of the vectors goes from this origin here to that new point. You see that? Let me just draw another one kind of random. What would happen if we added those together? Well, I need to draw, that's not very parallel. So I'm trying to draw this line parallel with that one. And then I'm going to draw, no, missed. And then I'm drawing this line parallel with that one, okay? So then the sum of the vectors is from this point to that new one out there. That's, the red is the sum of the vectors. That make sense? If you have 3 or more vectors, you add 2 of them first, and then you take the result, and then you add a third, you add a fourth, etc. So here's the example of adding these 3 vectors. They're going to add A and B first. So you add these 2 and you get R. And then they're going to take R and add it to C. And then they're going to get R prime. So R prime here in the purple represents the sum of all 3 vectors. Here's another example where we have 3 vectors of equal magnitude and they're going off in equally opposite directions. This is equivalent to a trigonal planar molecule where you would have an atom here and an atom here and an atom here and an atom here. And the atoms out here are more electronegative, and so the dipole moments are pointing towards the more electronegative element. So if I add A and B, I get R. And then if I add R to C, I get 0. Okay? So you could imagine one person standing here, and you've got 3 people pulling on you in these 3 different directions. If they're all equally strong, you're not going to budge. If one of these guys is stronger, then he's going to pull you off in that direction. So this is the general idea of adding vectors. Any questions? These are some common cases of adding dipole moments to see if a molecule is polar. And in all of these examples, we're assuming that the magnitudes of the dipoles are equal. So a linear molecule where you have dipoles in opposite directions, that's going to be a nonpolar molecule. If you have a bent molecule, that's going to be polar. A trigonal planar with equal dipole moments will be nonpolar. Tetrahedral will be nonpolar. But a trigonal pyramid will be polar. So I've got kind of a shortcut method. Let me show you that. So this is my shortcut to determining molecular polarity. It works like most of the time. A molecule is nonpolar if both of these conditions are true. There are no lone pairs on the central atom, and all of the atoms that are bonded to that central atom are either the same element or they have the same electronegativity. And the reason this works is because if there are no lone pairs, then those atoms are going to be equally distributed in three-dimensional space. And if the magnitudes of the dipole moments are the same, which is what condition 2 gets at, then they will add up to 0. So let's just look at a couple of examples of how this works. So if we look at water, okay, we already looked at water and we decided that it was polar, right? Well, there's the Lewis structure. Are there lone pairs on the central atom? Yes, there are. Condition 1 is not true. This is a polar molecule. How about carbon dioxide? There's the Lewis structure. Are there lone pairs on the central atom? No. Okay, we got condition 1. Are both atoms bonded to the central atom the same? Yes. So this is nonpolar. That's easier, huh? So one of the examples in that table showing the different things, what table am I talking about? I'm talking about this one. So here, this trigonal planar. If we have something like boron trifluoride, these would have lone pairs on them. But we'd look at this and we say that the central atom has no lone pairs, and all the atoms bonded to it are the same. We would predict that this is also nonpolar, and we would be correct. What if we swap one of these fluorines for something else, though? What if we make that, I don't know, a bromine? Is the electronegativity of bromine and fluorine the same? No. See, that changes the magnitude of that vector, the magnitude of the dipole moment. And so even though they're going off in opposite directions now, these two are stronger because fluorine is the most electronegative. And so now this is a polar molecule. Okay? So the vector addition business, if that didn't make sense to you, you're going to be okay. But you need to be able to do this. Okay? Any questions? Let's look at an example here. Determine if carbon tetrafluoride is polar.
No.
Correct, it's not polar. So, but we really need to look at the Lewis structure to decide that. So I'm going to skip all the counting of the electrons and everything, but we're going to end up with that. Okay. So this has a tetrahedral shape, and there are no lone pairs on the central atom. That means that the molecule is symmetrical. All of these elements are the same, and so we predict that this is nonpolar. Now, does this always work with my shortcut? Not always. I can think of an example. I think we did this one when we were talking about the effect of lone pairs on geometry. I'm going to leave all the lone pairs off the fluorines. My shortcut method predicts what? It predicts that it is polar because there's lone pairs, right? Bless you. But let's think about this. How many electron groups on the central atom? 6. So that makes an octahedral shape, right? Where are the lone pairs going to go? They're going to go on the top and the bottom. So we're going to have sulfur with a lone pair on the top and a lone pair on the bottom. And we're going to have a fluorine coming out this way and a fluorine going out that way. Fluorine going back this way and a fluorine coming out this way. What is the geometry of that molecule? It's square planar, right? The fluorine atoms all have the same electronegativity, so the strength of the dipole moment for all of these is the same, and they're going off in opposite directions. Is this a polar molecule? No, it's nonpolar. So my shortcut method doesn't always work. But things can be useful even if they don't always work, right?
So there's exceptions.
There are exceptions to the rule, and I'm not even claiming that it's a rule. I'm claiming, I just see it as an observation that makes it a lot easier to think about and works most of the time. But I'm showing you this just to show you that you need to be a little careful. It's like with the crisscross thing. You know, occasionally when you're crisscrossing charges, you end up with something that's wrong because you end up with SN2O4 or something, right? When it should be simplified. Yes?
Are we going to calculate the actual charge with the vectors eventually?
No, we're treating this very qualitatively. So we talked about, the magnitude corresponds to the difference in electronegativity. We're not actually going to do any calculations like that, but that's how you would do it. The other thing I'd like to point out is that I also gave you kind of a rule of thumb that, you know, when you're trying to decide if this bond is polar or not, usually if it's two different elements, it's going to be polar. But sometimes that's not true. And so you have to watch out for that one too. Oxygen and chlorine have the same electronegativity. So any oxygen-chlorine bond is going to be nonpolar. If these bonds, well, these are both nonpolar molecules. If we had something like this, I don't think this is really at all correct, but if we had chlorine with two lone pairs here so that this would be bent, chlorine and oxygen have the same electronegativity. If this is a nonpolar bond and this is a nonpolar bond, it doesn't matter what shape it has, the molecule is going to be nonpolar because they're sharing electrons equally all over the place. So that's another thing that could catch you, but not very often. The one that I would like you to remember, a carbon-hydrogen bond is nonpolar because the electronegativity difference is 0.4. And you run into this one a lot, especially in organic chemistry. There's carbon-hydrogen bonds everywhere. It can't be an organic compound if you don't have carbon-hydrogen bonds. So this is the one exception that I want you to remember. A carbon-hydrogen bond is nonpolar. You can't have a polar molecule if all of the bonds are nonpolar. Okay, does that make sense? The reason we talk so much about molecular polarity, and all we have to do is talk about it in a qualitative way, is because the polarity of a molecule has a big impact on its physical and chemical properties. And that has to do with how the molecules interact with each other. So if we look at water, okay, so water's a polar molecule. Water molecules will be attracted to each other, much like magnets are attracted to each other. Here you've got a partial positive charge and a partial negative charge, and they're going to be attracted, just like a south pole and a north pole of a magnet are attracted to each other. So I like this example. These solid marbles are magnetic, and these marbles are regular glass marbles. And I think we can all visualize this experiment. If you jumble all these marbles together, what's going to happen? The magnetic marbles are going to stick together, and they're going to exclude the glass marbles, right? That's what happens when you have polar molecules and nonpolar molecules together. What happens when you try to mix oil and water? Say you have Italian salad dressing, right? It's got oil and vinegar. Vinegar is an aqueous solution of acetic acid. You can shake it up, right? And then you set the bottle down and watch it, and what happens? It separates. And you can shake it up again, and it'll separate again. You could do that all day long. Why? Oil is nonpolar. Water is polar. Water is like these magnetic marbles, very attracted to other water molecules. And so, you can shake them all up, but then they're like, ooh, I'm seeking you out. And they're seeking out other water molecules to be together. And they exclude the oil. Polar and nonpolar substances do not mix together very well. This reminds me of high school. Lots of things remind me of high school. Do you remember cliques in high school? There were those groups of people. And, at lunch or something, you could try to get in there and be in the group, but they just kind of almost physically pushed you out, right? And you have a couple experiences like that, and you realize there's just no point in even trying anymore, right? They're just stuck on each other. And then you've got the glass marbles out here. So this is the nonpolar substance, and this is the polar substance. Any questions?
We use those properties to separate things.
You can use those properties to separate things, yes. And I think this is very interesting. How does soap work? So if you've ever gotten oil or grease or butter or Crisco or anything like that on your hands, you know that you can't just go to the sink and rinse it off with water. If you've got sugar, right, something sticky on your hands, water will take it right off. But oil or grease, no way. You need to use soap. Well, the grease will not rinse off in the water because it's nonpolar, and the water molecules exclude it. So soap is a molecule that has a polar head and a nonpolar tail. So these are carbon and hydrogen atoms, nonpolar bonds, and very symmetrical too. And so these tails will interact with the grease. And what ends up happening is that you get what's called a micelle that forms. So here's our blob of grease, okay? And then, I don't know, I'll use green. What happens is the tails, no, you can't see that. Maybe red. You can see that a little better. The tails of the soap molecules will get into the grease because they are also nonpolar. And then you've got the polar heads out here. The polar heads get along really well with the water because the water is also polar. And so the soap breaks the grease up into little tiny clumps that's surrounded with this polar head. The polar head communicates with the water, right? Interacts with the water. And so that allows this little particle of grease to move away and get away. I think that's a train. I don't think it's an earthquake. The screen is going up and down.
What do we do during an earthquake? We can't really get under it, can we?
No, we can't really get under anything. I don't know what we would do.
Get under the chair. Okay.
It just, yeah, depends on how strong it is. Because there's been a couple of earthquakes this semester, but we just didn't even feel them. The polarity, nonpolar polar stuff is a little bit like people speaking different languages, right? So if you had a group of Swedish people who only spoke Swedish and from Japan who only spoke Japanese. I'm picking on those two ethnicities because I'm of Swedish descent, my husband's of Japanese descent, and I'm hoping that that'll keep me from being accused of anything. So you've got this room full of people, and two languages, are they going to mix very well? Are they going to mingle and have a great time and get to know everybody? No. The Japanese people are going to speak Japanese to each other, and the Swedish people are going to speak Swedish to each other, right? What if you bring in some translators who speak Japanese and Swedish and can interpret for these people? Is that going to help mix things up? Yeah. So soap is like an interpreter. It speaks polar and nonpolar. And so it can help the grease get into the water and get washed away. Any questions? I like soap.